Welcome back for another AP Pre-Calc lesson. This is 1.7 Rational Functions and End Behavior. Rational functions are simply looking at fractions of polynomials. I have three examples on the screen right now that we're going to kind of preview. As you can see, polynomial top and bottom, right? We have coefficients, variables, and we have positive whole number exponents. Okay, those are our polynomials, and then you just have one of those top and bottom. And one thing that can start to happen is you get these weird ideas of what's called an asymptote. There's three types of asymptotes. We're going to slowly start to talk about each of them as we get into rational functions. First thing, just notice what an asymptote is. If I were to draw a line here, kind of where that graph levels out, that is an asymptote. Notice this asymptote is going side to side, right? That's what we call a horizontal asymptote. Asymptotes are generally the idea of where your graph levels out. What an asymptote really is it's a line that your graph or your function approaches, but it never actually crosses it. Okay, there are some limited exceptions to that, but that's the general idea for it. Okay, so one thing we can get is a horizontal asymptote. If you look at this next one, it doesn't just have that horizontal asymptote going across, but it also now has an asymptote going up and down on either of these two sides of this weird shaped kind of graph. Well, we still have an asymptote because our graph's getting close to it. It's kind of leveling out at those spots. But now this is what's known as a vertical. If I could spell, that would help. A vertical asymptote. There's really three different types of asymptotes that can happen when you have these rational functions. The last one here is what's known as a slant asymptote. So notice your line now. It does have a vertical one going up and down, but the slant asymptote comes in right here as your graph approaches it side to side, but it's still going up and down in this case. That is a slant asymptote. Today, the two that we're going to be talking about are slant asymptotes and horizontal asymptotes. We're not going to get in the idea of vertical asymptotes until we start looking at the next lesson, 1.8. Well, first, let's start talking about horizontal asymptotes. Horizontal asymptotes have three kind of cases that you can look at. These cases come about when you're looking at the actual function and the function's degrees on the top and the bottom. Case 1 says the degree in the numerator and denominator are equal. Well, what happens then, let's first start with an example. Let's say we have some function where our leading terms, right? If I want degree, I only care about the leading terms. Let's say I had like 5x to the third over 2x to the third. Well, notice the degree, 3 and 3, those are equal. Well, whenever your degrees are equal, what you end up getting for your asymptote, your horizontal asymptote, is a ratio of their coefficients. The reason that works is if you were to look at infinity for your x, right? If you were to kind of think about the abstract idea of plugging in infinity. Well, infinity to the third over infinity to the third, those weights kind of cancel each other out. You basically have something dividing by itself, and all you would end up getting is just a value of 5/2. So if you think about the end behavior, the far left or the far right at where x is an infinity, the infinities cancel out, and all you have left is the 5/2. Well, let's carry on that idea to degree in the numerator is smaller than the degree in the denominator. So that's telling me that the top has a smaller degree than the bottom. Let's say x squared over x to the fourth. Well, if you were to have infinity squared over infinity to the fourth, the bottom of that has much more weight, right? If you were to simplify that fraction, it'd be 1 over x squared. And if you think about the far left, the far right without bound, that value on the bottom is going to be very, very, very large. Well, if you take some number and divide it by a really, really large number, what you end up getting is a number close, extremely close to 0. So what we'd end up finding is there's a horizontal asymptote at y equals 0 in that case. Third case, then, is when we have the opposite, where the numerator now, the top, is larger than the degree in the denominator. Maybe something like 7x to the 5th over x squared. Well, if you were to simplify that, I don't even need the 7 in front, really, to think about this. But if I were to simplify that, that's now x to the 3rd over 1. And if you think about x without bound, what ends up happening is it goes off to infinity. Whether that's positive infinity or negative infinity, you would have to figure out by thinking about the simplified version of the fraction or your leading terms. You would look at the end behavior then. So for example, if I looked at this simplified version of x cubed, I would notice x cubed is 1 positive, but it's also an odd exponent, odd degree now. So I know the end behavior on the left would be going down, the end behavior on the right would be going up, and then you could make your limit statement about where the ends are going. So that last case, case 3, you don't have an asymptote or horizontal asymptote. You instead have to look at the end behavior and whether your function's going off to infinity in which direction. Let's start to break this down looking at some examples. Looking at this first graph, you can see the asymptote is at y equals 2, but let's prove that. Well, what I know is I want to look at the leading terms, and my leading term on top is negative 4x to the 4th, and on bottom it's just 2x to the 4th. So if I were to just look at those two in some sort of fraction and start to compare their degrees. Well, the degrees in this case end up canceling, and all I'm left with is negative 4 over 2. Well, remember, case 1 said if your degrees are the same, all you care about is the ratio, the fraction of the coefficients, which is negative 4 over 2. I believe this is actually a positive 4 over 2. That's a mistake. That's a typo on my end. Okay, but having that 4 over 2, then you would see that that value does simplify to 2. That tells me the horizontal asymptote is at y equals 2. One thing you could do with this, though, is talk about the end behavior of this function. We know that on the left or the right side, our function is going to go off to infinity on the left and the right. So what's happening, though, with the y values? Let's talk about that. So let's first look at the left side as x goes to negative infinity of our function f of x. Where are the y values going? Well, if you look at the left side, it levels out at the horizontal asymptote. So it's not going up, it's not really going down, it is minimally changing technically, but really what's happening is it's getting infinitely close to that y value of 2. So we're going to say, as it goes off without bound to the left, your function is going to a value of 2. Same idea with the right side then. Our function on the right is also going to the y value of 2. Now we have the limit statements as well as our horizontal asymptote. You can see that in the graph, it is y equals 2 as well. There is case number 1 for us. When the ratio or the degrees are the same, we use the ratio of their coefficients. Next case. This function's a little bit more complicated for us to analyze. The reason is I can't just look and find my leading coefficient right now, or my leading terms, I should say. Well, let's start to break this down. If I were to multiply all of these x's out, the top I would have x cubed, as well as the leading coefficient there of 0.3. And the bottom of my fraction, if I multiply all of those x's out, I would end up having x to the 4th. Notice the degree on the bottom is larger than the degree on top. Well, what ends up happening is if you looked at that towards infinity, the bottom gets really, really big, and the top doesn't really play a factor anymore then. So if the bottom is much, much larger, that tells me I would have a horizontal asymptote at y equals 0, which you can see that on our graph. And again, you could talk about the limit, the end behaviors as well, which if you look at the left and the right side, they're not going up, they're not really going down, they're just going along with the asymptote there at 0. So you do get both limit statements for the end behavior where the y values are now 0. That is case number 2. Case number 3 then is, well, okay, what happens if the top of your fraction is now larger? Well, let's see what we actually have. Well, x and x squared on top for our leading terms is x cubed. On bottom, I'd have 2x squared. And now I notice the top does have that larger degree. And what we said is if the top has the larger degree, it's going to increase towards infinity. So we need to know what is the end behavior of its simplified form going to look like. And if I looked at that, I'd end up getting 1/2 x. We're going to talk about what that value actually gives us in just a moment. But 1/2 x, I do know that is a positive function where the degree of it is odd. So it's positive and odd. Again, that's the similar example we saw earlier. That'd mean the left side goes down, the right side goes up. And as you notice with the graph here, it does that without bound, meaning it's going to go off to one of the infinities. So I don't have a horizontal asymptote, but I do need to create those limit statements to talk about the end behavior. The left side of this function, we said 1 by the graph, it is going down forever. But 2, you can also notice it's going down based off of this analyzation of end behavior. The right side, again, by the graph does go up, and using our analysis does go up towards infinity as well. Those are all 3 cases for end behavior, mainly horizontal asymptotes included. But there's one other idea that we need to talk about for this last case, which is a slant asymptote. Slant asymptotes occur in a very, very specific time. Slant asymptotes occur when the numerator has a degree that is strictly one larger than the degree on the bottom. So the numerator degree is one larger than the denominator's degree. That is when you get a slant asymptote. So just like this example we just saw, it was x cubed over 2x squared. Notice the top of that, the degree on top, is one larger than the degree on bottom. You will always get a slant asymptote. A slant asymptote then will occur and be parallel to the line in which this fraction simplifies to. We said this fraction simplifies to 1/2 x. We know that our slant asymptote has to be parallel to that. Notice this graph, that's exactly what you end up seeing. If you were to kind of look at this asymptote, maybe erase some of the lines I already drew, notice it is increasing at about 1/2. Right? We're going up 1/2, up 1/2. That is the slant asymptote that we are parallel to. We might move this slant asymptote up or down by changing this function, but that is the idea of being parallel to it. That is our preview of all of the different types of asymptotes. We'll continue this conversation in 1.8, analyzing rational functions to a whole nother level, but first just figuring out what they are and learning about these different asymptotes. That is 1.7 for AP Pre-Calc. Thank you for watching.